Now coming to the one-dimensional consolidation test, that is also known as oedometer test. By using this test, we can determine the consolidation settlement of any soil under any pressure. Now, this is the specimen of consolidation test. Here, the specimen size is like this. 60 mm is a die of the specimen, and 25 mm is the size of the specimen. Now, this specimen or this soil sample is prepared in the in a O-ring, where the size of the O-ring is similar as the soil sample. That is, diameter is 60 mm and height is 25 mm. Now, this specimen or the sample is placed between two porous stone, where we can see from this figure, this is a bottom porous stone, and this is a bottom porous stone, and this is a top porous stone. Between this two porous stone, this soil sample is placed. This is a loading plate, and this is a dial gauge, by which we can measure the vertical settlement of this soil sample. Now, after preparing the soil sample and placed it in the O-ring and in the experiment setup, an initial sitting pressure of about 0.05 kg per centimeter square is applied to the sample to ensure that there is no swelling. The sitting pressure, this sitting pressure, 0.05 kg per centimeter square, is kept for at least 24 hours. Now, after applying the initial sitting pressure 0.05 kg per centimeter square for 24 hours, there will be increment of load. The first increment of load is 0.25 kg per centimeter square, and is then applied to the specimen, and corresponding dial gauge reading is taken after like 0.25, 1, 2.25, 4, 6.25, up to the 24 hour, up to the 24 hour, and after that the second increment of the load, that is 0.5 kg per centimeter square, is then applied. It is usually practiced to double the previous load. The successive load usually applied are starting from 0.25 kg per centimeter square, 0.5, 1, 2, 4, 8, up to the 16.0 kg per centimeter square. Now, after consolidation under the final load, that is the final load here, already have shown you. The final load is 16.0 kg per centimeter square. So after consolidation under the final load, the increment is complete. The load is reduced. Then the load is reduced to 1/4 of the 16.0 kg per centimeter square. So that will be 4 kg per centimeter square. And this part is the unloading part. After reaching to the maximum load, that is 16 kg per centimeter square, now the load is reduced to 1/4, that is 4 kg per centimeter square, and it is allowed to stand for also 24 hours. It is also allowed to stand for 24 hours, and this way sample take water and swell. This is the schematic diagram of the one-dimensional consolidation test, and that is oedometer test apparatus, and this is the actual apparatus, one-dimensional consolidation apparatus, that we generally used in our laboratory. Now, after applying the final load, that is 16.0 kg per centimeter square, the load is then the unloading process is started. Now then load is reduced to 1/4. Now our final load was applied load was 16 kg per centimeter square. Then 1/4 of that, that is 4 kg per centimeter square load is then applied. That means we will reduce 12 kg per centimeter square load, and the swelling of the soil is recorded after 24 hours. Again, the load is reduced to 1 kg per centimeter square, that is 1/4 of 4 kg per centimeter square load, and the swelling is noted after 24 hours. Finally, it reduced to initial setting pressure, that is 0.05 kg per centimeter square, and corresponding swell is recorded after 24 hours. Now, throughout the test, the water in the water bath should be filled with water. Now, immediately after completion of the test, the weight of the soil sample is taken, and the sample is then dried in an oven, and the dry mass of the sample and water content is determined. Now, by using this dry mass of the sample, we will determine height of the solid, H suffix S. Height of the solid, we will determine height of the solid by using this dry mass of the sample. Now this is the table. This part is the observation part, and this part is the calculation part. This observation part is generally we record during the progression of the test. Here we can see in column 1, here is the applied load. The applied load is initially it was 0, after that 0.5, 1, 2, 4, 8, 16, up to 16. This is the loading, and after that I have told you in the explanation of the test that after 16 there will be the reduction of the applied load by 1/4. So 1/4 of the 16 will be 4 kg per centimeter square. After that 1 kg per centimeter square, and finally that will be 0. Now corresponding to 0, we have recorded the dial gauge reading is 490, and after applying the 0.5 kg per centimeter square load, after completion the 24-hour period, the dial gauge reading become this 482. Now from this we can easily find out the change in thickness, that is 0.08 mm, and here minus symbol is used because there is the reduction of the height of the soil sample. So in this same process we will find out the change in thickness corresponding to 1 kg per centimeter square, 2 kg per centimeter square. So we can easily find out, and here it is the swelling after 16 kg per centimeter square. When we reduce the applied load to 4 kg per centimeter square, then there will be the change in the thickness in positive direction. That means there will be swelling. So by the same method we will find out the swelling. That means change in thickness in positive direction for 4 kg, 1 kg, and for 0. Now this is the observation part, and after that we will go to the calculation part. This calculation part here, at first we have H. Here H is the height of the sample. Initially we have 25 mm height of the sample, 25 mm. In this slide we can see height of the sample is 25 mm. So initially at 0 applied pressure, the height of the sample is 25, and after applying the pressure 0.5 kg per centimeter square, here is the change in thickness is 0.08. So just we have minus this 0.08 from 25 kg per centimeter square. So thereby we have this value 24.92. 25 minus 0.08, and that is 24.92. So by this method we can easily find out the height of the sample corresponding to different applied load. For 1 kg per centimeter square, for 2 kg per centimeter square it is 24.41. So we can easily find out for each and every load, for loading and unloading for both. Now here this is the H minus Hs. This is the difference between the total height of the sample and height of the solid. Hs is the height of the solid. Now height of the solid is a constant for any experiment or any soil sample. Here height of the solid we can find out by using this formula. That is height of solid equals to Vs by A. Vs means that volume of solid divided by A. So volume of solid we can write it by using this formula. Vs equals to Ms divided by G into rho W. Ms means dry mass of sample, G means specific gravity of that sample, rho W is the density of the water. Now by using this formula, so here we already know the dry mass of the sample. Here we can see we have already know the dry mass of the sample, and we know we will have the specific gravity, and we know the cross section area A. As we know the diameter of the sample is 60 mm, so thereby we can easily find out the cross section area A. Now by using this formula we have Hs, and from this column we have H. Now we can easily find out the difference between H minus Hs. Okay. Now finally we need to find out E, that is the void ratio. Now void ratio is the volume of, here you can see the void ratio is the volume of void by volume of solid. Now volume of void that is V minus Vs divided by Vs. Now by using this formula we can easily find out the void ratio. Here V is volume of the sample, Vs is the volume of the solid. Now volume of the sample, we derive this volume by cross section area and H that you know, and here it is the final formula. E equals to H minus Hs divided by Hs. So here we have used this H minus Hs divided by Hs. Here we know H minus Hs from this column, and height of solid is constant. Here height of solid is 14.27 mm. So by using this method we can easily find out the relation between applied pressure and the void ratio.